So in terms of problem set number 9, yeah, it's number 9 already. Any questions on that? Thoughts? What was the hard one? Was it number 3? Was number 3 the hard one on that one? Okay, so people are nodding. So I take that to be a good sign. That tells me that the skills of how to find eigenvalues, how to find eigenvectors, how to put those together, that's not the hard part, which is good, because if that's the hard part, we got big problems. The hard part should be, how do I put it together? How do I connect these things? And how do I connect it to a real world situation? So if we take a look at that number 3, I give you the coefficient matrix. I give you the differential equation as a matrix equation. And then I don't ask you to do anything. I don't ask you to solve it. I don't ask you to go through the motions of, doing those skills. Instead, this question is all about interpreting what's going on. And I think, this is my hunch, what makes this problem particularly difficult is that the y variable is population, but the x variable is not population. It's how far above or below the equilibrium is the population. It's the deviation. That's the fancy name for it. The deviation from equilibrium. So x can be both positive and negative, right? But the y variable can only be positive because it's an absolute scale of 0 fish to however many fish. So I think that's what makes this hard, is because we're comparing two very different things. They're both about fish populations, but they're not the same thing at all. So I'm curious, what did you make of what sorts of species interactions correspond to the above model? That is, whether the introduced fish have the effect of increasing or decreasing the native fish population. How did you go about answering that? I didn't tell you what to do, so I just said, here's a question. So knowing that you had all the tools available to you, what'd you do? So you skipped it. You just wrote, this is a stupid question, I refuse to answer. And you moved on to the second part. No, of course not. So how did you go about answering it? I mean, yeah, okay, you used words, but what evidence did you use? Did you look at the equations? Did you make a DE plot? What'd you do?
Well, for me, I just looked at the equation and saw the plus 0.2, just said it increased.
So that equation, of course, the top equation, corresponds to, if you want to make it x, so it's a negative, x population has a negative impact on dx dt, and the y population seems to have a positive impact, right? So the presence of those extra fish this extra species of fish seems to have a positive impact on the native species. What does that mean must be going on between the native population and the introduced species? Think like a biologist, think like an ichthyologist. What does that mean about our fish?
That the introduced ones are probably prey to the ones currently in there?
Probably there's some kind of the prey relationship, right? So that would be my guess, right? I don't know, but that would be my guess based on the model. So if you were talking to, let's say you're the engineer or you're the mathematical biologist or whatever, and somebody comes to you and goes, we have this model, you'd look at it and you'd say, just to be clear, is the introduced fish the prey of the existing species? Because that's what it looks like in the model. Alternatively, what are some other ways that it could actually be in reality, but still look like that? So maybe they're not new prey. What else could they do?
Maybe there's like some symbiotic relationship.
Yeah.
That helps them out. I don't know.
Yeah. So, and this is where we're like, I don't know how much biology you know, but he mentioned the word symbiotic relationship. What does that mean?
They kind of just help each other out, like without eating them, like kind of.
What's a good example of? Do you have an example of what that might be in nature?
I can't think of anything right now.
Anybody else? You guys have had maybe some biology. Does it sound familiar? Symbiotic relationship.
Termites have bacteria in their stomach that digest wood.
Yeah.
I believe.
Yeah. As a matter of fact, we all have, you and I and all of us have all kinds of bacteria in our guts that if we didn't have them, we wouldn't be enjoying the large amount or large variety of food that we eat. There's a lot of stuff that we consume that we have absolutely no mechanism for digesting on our own. It's only because we have a symbiotic relationship with the bugs in our gut. Right? So that's a great example. Great example. Okay, so the second question says, according to the model, will the population of the native species return to equilibrium if the introduced species is not present? And of course, the most important point, I don't know if you've caught it, but I like to emphasize, so I italicized, justify your answer. So that's me saying, you can't just say yes or no. The important part is, how do you know? What are you basing this on? So what did you do for part B? What was your approach?
Well, I said it would go back to equilibrium.
Okay, but based on what though? What
Because
did you
I
do?
kind of figured that if there wasn't any working off the dx/dt equation, if there wasn't any y, it would be, let's see, e to the negative power, which over time will e to the negative t power,
Okay.
which over time will go back to 0.
It heads back to 0. So notice it doesn't mean it's bad for the existing native population, because remember, X doesn't represent the size of the population. It represents how far away from equilibrium it is. And so if it's decaying back to 0, that means it's decaying back to equilibrium.
Yeah,
So
I figured.
terrific example. You read the equation. I looked at dx dt, and this is what I see qualitatively. I didn't have to solve it to know that. I could look at the dx dt equation. What else could you do besides look at the equation? You got maple. How could you use maple to answer this question?
Use a plot,
Such as?
like the plot.
Yeah,
where-
take a look at the phase plane, right? The phase plane should show you kind of at a glance what's going on with every possible solution curve. Because if you can plot it on the phase plane, you can kind of follow the arrows and see what does it look like. And so when you look at does anybody have it handy on their Maple right now that they could share the screen and show us? Let me make sure that my screen sharing.
I got mine.
Okay, plop it up there. Let's see what the phase plane looks like. Okay, so we have a phase plane. As a matter of fact, we have what we would call a phase portrait, because we have a whole bunch of different initial conditions that showcase what's going on the phase plane. And this came up a couple of times in the homework assignment. So make sure you know the difference between a phase plane, which is just the field of arrows, and a phase portrait, which is demonstrating what solution curves genuinely or generally look like in a bunch of different places. So based on what you see here, can you, using your mouse, walk us through how do you know that introducing the other fish species is going to be a good thing for the native population?
I'm not really sure.
Okay,
I wasn't entirely sure what this graph meant.
So let's think about it this way. Where on that phase plane are possible solution curves? In other words, what values of x and y can we be looking at?
Well, I had one that was 2/11ths for the x and 1 for the y. That was one of the straight line solutions.
Okay, so it looks like it's that one, right?
Right here.
So it looks like that one's sitting on a straight line solution. So we can look at that because it's positive x and positive y. But can we have negative x and positive y? Is that allowable in this situation?
No. Well, not for the straight line solutions, no.
Well, yeah, it wouldn't be on the straight line, but
Can be more like what this one.
But let me back it up even further. Is a negative x value, does it make sense in this context? A negative x and a positive y. Does that make sense in this context? It's not a trick question. It's
Sure.
just, So what does X represent again? Remember in this problem?
The difference of the population of the native fish from equilibrium.
So positive values are okay, but so are negative values for X, right? So we
So I
know
guess
anything across the y-axis on both sides of the y-axis is fair game. How about above or below the x-axis?
just above, because y has to be positive.
There you go. So the point that I was getting at is when I say for any possible situation, the only possible situations are the ones that are above the x-axis. Anything below the x-axis doesn't make any sense. So even though you have solution curves down there, it's nice, but those have nothing to do with our situation. So all of the solution curves that are above, yeah, you kind of scoot it down, and all the solution curves that are above the x-axis, what happens as long as y is positive, as long as y is above 0, what happens to the solution curves over time? Where do they go?
It looks like both the x and the y increase over time.
Okay. So what does that mean for the fish population, the introduced fish population? What's it going to do?
Oh, I see. It makes the population keep growing.
Yeah.
Oh wait.
Yeah, you're right. The introduced fish population will continue to grow. It's a good thing for that fish population. And so will the X population. And this is important. So even if we started off with a, below the equilibrium for the X, right? Even if that population was, the X value is negative, that means we're starting below equilibrium. Our fish population, our X direction fish population, that's going to grow. Grow. And so introducing the introduced fish, that's a good thing for the native population across the board, no matter what, no matter where you start. If you have a positive Y value, it can only mean good things for the native population.
Yeah, I see that now. I wasn't
That makes sense?
sure what it actually meant.
Yeah, and that's why I wanted to talk about this problem in particular, because there's like extra layers of making sense of what's going on with the phase plane. And the phase plane allows us to kind of qualitatively make that judgment call. There's no place on the phase plane that makes sense for the problem, above the x-axis. There's no place on the phase plane that's bad for the x population or bad for the y population. It's just good all around.
Yeah, that makes sense.
Cool. Thank you for sharing your Maple document. How does that make sense, folks? How are we feeling about that? Is that good? Somewhat. Okay, Bryce. Here's your chance. I want you to, in your own words, explain what the phase plane for that problem tells us about the long-term outcomes for our two fish populations. Take a stab. Now, if you want, you can wait until after class, watch the video where you explain it, and then come back in time and then just no, that doesn't work. You're just gonna have to explain it now. Go ahead.
Well, the new fish would just exponentially grow. It would just grow nonstop. But I would imagine, I think the quash kind of showed that the native fish would go to equilibrium.
It would definitely go towards equilibrium if you started below equilibrium. So if you started on the kind of the left-hand side of things, it would head towards x equals 0. But those curves don't stop at x equals 0. They just keep going through, right?
Past it.
So we have to think of the phase plane as being both the horizontal as well as the vertical. The vertical is what's happening to the introduced fish population. The horizontal is what's happening to the native species, right? So as we see those curves kind of going up like this, we can't think of that as like a population curve, like, oh, we're seeing it grow over time. There is no time dimension on the phase plane. We don't see time. What we're seeing is what's happening to X and Y, the two populations in conjunction, right? So any point on the phase plane represents a moment in time. The curve represents what happens from that moment. If you play the clock forward, this is what happens to both the X population and the Y population. Does that make sense? It's wrapping your head around seeing the phase plane is tough. So one of the things that we can do that helps is instead of relying just on the flat two-dimensional phase plane, we can turn it into a phase space, which allows us to then say, oh, I'm going to make the time dimension come out of the screen three-dimensionally, and then I can see what's happening to the curves. You can actually see that exponential growth over time. You can actually see what's happening to it. But that's a different it's a different graph. That's not the phase plane. That's the three-dimensional view. Remember that diagram at I think it's the beginning of chapter 2, or like the second section of chapter 2, where you see the phase plane is kind of the shadow of the three-dimensional curve moving in space. So if you want to see time, you have to look in that third dimension. But the phase plane itself doesn't show you time. It shows you the relationship between the dependent variables only. Yay. Okay, how about the rest of it? Not just that problem, but the rest of the problem set. Any stumpers, any questions on that? I tried not to make it too heavy with by hand, right? Everything wasn't by hand. There were only a couple of places like number 4 where I really wanted you to struggle with a by hand problem with imaginary eigenvalues. Don't worry, I won't make you do it a lot. I just want to make sure you know how it works. Okay. 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 I get you. I'm reading you. I'm reading you. So here's what we're going to do. We will step away from that problem set and turn our attention to the 3.5 and 3.6 classwork. Now, I know there's 2 groups that are down 1 person. So I think what I'll do is I'll probably combine those 2 folks into 1 group. And if people show up, like Chris said that he might show up later on, and what I might do is add him to a group later on. But for starters, I'm going to have us join forces to work on the, what's the word I'm looking for? There we go. Join forces to work on those classwork problems. And you'll notice we've got everybody for the 3.6 is doing the same pair of problems. There's method to my madness here. I want to make sure everybody can do those. So let me assign these rooms here. Stephen. Who's in the next one? Chris, Austin. Austin, you're going to be with Bryce. Then we have Emma and Paul, John and Quentin. Okay, so I've got you in your rooms. How about we head into the rooms? I'll pop into the different rooms and check on things, but aiming for being back together by at least by 7 o'clock, if not before. Fly, be free. And I will pause the recording. Okay, so we're back from our groups. So let's take a look at the 3.5 classwork number 1. Who had classwork number 1?
We got it.
Fire away.
Okay, so initially, let's share screen. Where are we at? Okay, so initially we started out, we had a character, we were given what lambda equaled, and lambda equaled -6, and for part A, we were required to find a characteristic polynomial. So since this was a repeating lambda value, or repeating eigenvalue as what it's technically called, we set lambda, since lambda equaled -6, lambda plus 6, lambda plus 6, and we were able to derive our characteristic polynomial, which was lambda squared plus 12, lambda plus 36. And then the next step, they wanted us to come up with our differentials. So by doing that, we simply backtracked even further, and we had -6 minus lambda as part of our, I can't remember what it's called, our
modified coefficient matrix.
Modified coefficient matrix right here. And then we also noticed since it was plus 36, lambda plus 6 already gave us 36. We couldn't have anything on the end. So we had 0, 0 for those two parts of it. And this is what we got for our d's for part B. We got d over dt x of t equals negative 6xt, and d over dt y of t equals negative 6yt.
Okay, so hold on real quick before you go on. Just to verify, you said very wisely that you knew your characteristic polynomial had to look like that, and so that means that the b and the c in your coefficient matrix had to be 0. Is it true that both of them have to be 0?
No, I led Steven astray by telling him they did it at one point, and then I had to correct myself. But only one of them has to equal 0.
Yep. So it could be that in the top equation, b is equal to 0, or it could be in the bottom equation, c is equal to 0.
Right.
Either way. But notice, whichever way you do it, think back to chapter 2, whichever way you do it, as long as one of those is equal to 0, you actually are guaranteed to have a partially decoupled system. Convince yourself of that real quick. Take a look at that coefficient matrix. If b is equal to 0, then that first equation is fully decoupled. If c is equal to 0, then that bottom equation is decoupled. So you have a partially decoupled system no matter what. So cool, nice. Continue.
If they're both equal to 0, then that means the system's completely decoupled.
Fully decoupled. Okay. Yep.
Okay.
Which, by the way, that's the way mathematicians will tell you that they're breaking up with you. I was thinking that maybe we could become fully decoupled, and if they say I'd like to become partially decoupled, that means they're open to a open relationship. I'm just letting you know that's how mathematicians talk like that. So.
I'll give you a 6.5 out of 10 for funniness on that one.
Hey, I was trying really hard. Sorry, nose blowing in the background. So part C.
And part C, we have to use the ballot. So we started off with what is it? So basically, it's b subscript 1 equals a, and a represents our matrix that we have right there, and then minus lambda times I represents this matrix right here, which is 1, 0, 0, 1, and then times subscript b subscript 0. So b1 equals, that's our matrix, minus lambda, which was from up here, negative 6, and then times that. And so this is where I got a little confused and stuff in the notes, because like you said, is I could have one of these numbers be a non-zero. But when you would do the ballot, wouldn't that affect what x of 0 or y of 0 would be if it was a non-zero number?
It would basically be a multiple of x sub 0 or y sub 0, depending on which one was non-zero. Yeah, absolutely. The way you set it up, the system of equations that you chose has that v1 is equal to 0, 0. In other words, it's non-existent. That part of your general solution just doesn't matter. It doesn't do anything.
Okay, so that would just equal 0. So our final equation would be y of t equals e to the negative 6t, and then x of 0, y of 0, and then plus t e to the negative 6t. That was a key part of how the ballot thing works with the extra t on the out front, and then 0, 0, which technically this wouldn't exist.
Yeah, it doesn't do anything to the solution. And so the general solution, you'd only need the first part of it. And if you look at that first part of it, it's telling you your general solution is exponential decay in the x direction and exponential decay in the y direction.
Okay.
And the coefficient for both of those is whatever your initial condition is. That is the simplest possible system of differential equations. Incredibly boring system of differential equations, right? Fully decoupled system. Yeah. And so if I were to say, okay, now go back and change one of those zeros to 2, then you could pretty easily kind of track that through, and you'd find out that, oh, suddenly the result, it's what I'm looking for, the general solution, there we go, does have 2 terms. The second term would not just be 0, 0 for that matrix.
It only have 2 terms for one DE though, right? The
Exactly.
other DE would still be
Yep. The solution for either X or Y would have two terms, but the other one would only have one term. Yep, you're absolutely right. Yep. And because we know it's guaranteed to be at least partially decoupled, we know that we can solve this using separation of variables and the technique that we learned way back in chapter 2. So, yep. Nice work. Good job.
Thanks.
Any questions on that one? I know some of you, I'm not naming any names, but some of you have some videos to watch. So if you see the word ballad and you're like, what the hell does that mean? That means you didn't watch the videos. It's one of the ways that I set it up so that I'd know. So how about number 2? I know there were 2 groups that had number 2. So how about we let, I don't know, who is one of the groups that had number 2 here? Okay, so you guys are going to take the first 2. So John and your partner, why don't you do part A and part B, and then we'll take a look at part C and part D with Paul and Emma.
Okay. Here, we'll get rid of part C and part D. Okay, so part A. Here, let me go to the actual. Okay, so when we first learned about eigenvalues, we defined them as being special values that, when subtracted from the A and D parameters in any coefficient matrix, yield a determinant of 0 for that modified coefficient matrix. But what happens when the coefficient matrix already has a determinant of 0 without any modification? For example, this matrices right here, this matrix. And using Maple, what are the eigenvalues and associated eigenvectors for this coefficient matrix?
Ta-da!
These are them.
So notice that if you were to calculate the determinant for that matrix, it would be diagonally 4 times 2 minus -2 times -4. And so that would be 0. It's already got a determinant of 0. So what's special about this? When the determinant already equals 0, what does that guarantee we're going to have?
That, I mean, that's, then we're gonna have the
It's right there on the screen. So what's special about this?
vector. No, I'm sorry. The equations.
So what's unique about this system? Before 3.5, we'd never run into a system that had eigenvalues of 0, right?
Yes.
And so that's what we're seeing. For the first time, we're seeing a system that already has a determinant equal to 0, and that's always going to produce an eigenvalue of 0, right? 1, but not both. 1 is equal to 0.
Did I lose you? Hello?
Yeah, no, I'm right here.
Okay, you're good. Okay.
Well, I mean, that's a...
Sorry, you were in and out for a second, so I didn't know I lost you or anything. So, and then
okay, part B.
B was state the system of differential equations associated with this coefficient matrix in terms of the dependent variables x of t and y of t, and that is right here.
Marvelous job. Okay, take it away, Paul and Emma, for part C.
All right, let me share my screen here. Okay, so for C, we found that they are linear multiples of each other.
Okay, what the heck does that mean?
It means like they're like if you, well, in this case, if you multiply dy dt by -2, you get dx dt.
So each term, each variable's coefficient is the exact same multiple as the other variable's coefficient, right?
Yeah.
So multiply the top equation by -1/2, you get the bottom equation.
Yeah, which that would do. And that was also stated because one of the eigenvectors was 0.
Eigenvalues. Yep.
Yeah, eigenvalues.
Yep. As a matter of fact, putting these pieces together, if the equations are linear multiples of each other, you're guaranteed to have a 0 as an eigenvalue. But that also means that your coefficient matrix has a determinant of 0 to begin with. So those three things are always true. So if I tell you, if I say, hey, there are these two equations, you know, dx dt equals 2x plus 2y and dy dt equals 5x plus 5y, you're going to look at that and go, oh, I know that that matrix is going to have a determinant of 0. I know it's going to have an eigenvalue of 0, guaranteed. It's just the way it works.
Okay, and for part D, we did a D solve and got the general solutions
Nice.
of these two. And from there, we plugged in the initial conditions and figured out what K1, well, there's supposed to be K1. I have C1 here.
That's okay.
We found out that K1 was 1/3 and C2 was 2/3. And so we plugged that into to get the X of T and Y of T and then made the matrix equation.
So notice because we have a 0 for an eigenvalue, that means the part that's sitting in front of the K1, right? That's K1 times e to the 0.
Which is just 1.
Which is just 1.
Yeah.
So if one of your eigenvalues is 0, then it doesn't exponentially grow and it doesn't exponentially decay. It just sits there. So you have a straight line solution, but it's not going away from the origin or towards the origin. It's just sitting there. If you're on that line of straight line solution, it doesn't go anywhere. So go ahead, sorry.
That makes sense.
Cool. Cool. And the only thing that I would say is, just as a refresher, a reminder, you went through and you solved that, all of that by hand. Could we modify your dsolve command to get matrix or to get Maple to solve the whole system with the initial conditions for us in one fell swoop?
We tried that and it came up with something that didn't make any sense.
Go ahead and try it. Show us what you got, because this is important for people to see in this case. So, yep.
Okay, so we put in x of
Oops.
x of 0 equals 1 and y of 0 equals 0.
And Maple says?
Maybe we did it wrong, but it didn't. Oh, that's not what came up before.
It could have been a typo in the code. But notice, Maple gives you the parametric form of the solution equation. And that should track, and that should look exactly like it belongs to the matrix form of the solution later on. So you can see the parametric form of the solution and the matrix form of the solution. They're the exact same thing.
Yeah, before we came up with like a x of t equals 0 and a y of t equals 0. It didn't make any sense, so we took it back out.
That's weird.
I'm not sure what happened there.
That is weird. Okay, so that was question number 2. How about question number 3? Who had question 3?
That would be me.
Fire away.
Guns blazing. Well, question number 3 was asking, what was it asking? I don't even remember.
The origin of the phase plane is always the only equilibrium point for any system of linear differential equations, true or false?
And I said false.
False.
0 is always the trivial equilibrium solution for linear differential equations. But in the notes, there also was a way to find non-trivial solutions via this lovely thing here, this lovely system. So I did that, putting in the code right here. And as you guys can see, there is the equilibrium solution is not just at 0, but instead we have infinitely many equilibrium solutions in this very blank area here.
Yeah, and you can see the arrows are pointing kind of in opposite directions. On one side they point one way, the other side they point the other way, but there's like no arrows drawn right there. So what do you make of that?
Well, as you guys can see, I have 2 colors missing here in my phase portrait. So to figure out what happened to those, I did a 3D plot, and boom, you can see right here, there are your two colors that fall in the equilibrium solution on the 2D plane. But when you go to 3D plane, you can see there they are. And also you can see this green line here falls into that area of equilibrium solutions. But as you see in the 3D plot, it also is heading in the same direction as these other two. So answer the question, it's false.
So there's infinitely many equilibrium solutions. We just can't see them on the phase plane because remember, the phase plane doesn't show us the time dimension. It only shows us the shadow of the entire space smushed down in the time dimension. And so if you rotate it 90 degrees so that we are seeing the X and Y, yeah, keep going. Yeah, just shift it up a little bit. There you go. So what you're seeing right there is, well, it's a little bit backwards because the X is going negative to positive this way. But if we can rotate it, it's okay. If you rotate it, spin it around the other way. There you go. Keep going. There you go. That is going to be just basically a copy of, scroll up, a copy of this right there. That's the phase plane that we're looking at. Those three curves are the ones that we see, but on the 3D plot, you can see just the tiny little dots that are the blue and the red. On the phase plane, they don't show up because a point doesn't take up any space. But yet they're there. They're just coming straight out of the phase plane at you. They're only moving in time. And as Austin pointed out, that lime green colored solution, it looks like it just kind of stops up there. But it's not. It doesn't stop. It's coming zooming out towards and then bends away. So what we can see with the 3D plot is that things can move in time even if they don't move with respect to the dependent variables, even if the dependent variables don't change at all. Along that equilibrium solution or along that straight line solution of over 1, up 1, right? Any point that's on the line, y equals x, doesn't move at all. Is that pretty good?
Yeah.
I tried to do an example in the notes, and I've got the Maple document that's published. You can check those out as well. You can see them on there, so that should help. I hope. Did I post the Maple documents? Yeah, I did. Okay, whew. I checked. I had to remind myself whether I posted those or not. So cool. So that was number 3. How about number 4? Ooh.
I had number 4.
Fire away.
Oh.
Yes.
The question asked, is there any possible 2 different systems of linear differential equations that have the exact same eigenvectors?
Nice.
So I didn't really care about the eigenvalues because it was only caring about the eigenvectors. So it took a lot of trying random vectors, but I ended up thinking about what is complete opposites but still the same numbers. So I was like, well, if it's got the same numbers, if I can make a complete opposite, so which would mean all negative, 2 different systems of linear differential equations, but they gave me the same eigenvector.
So putting this together now, having the same eigenvectors means what about the phase plane? When I look at the phase plane, the DE plot, what am I going to see? If I plotted both of those systems, if I plotted their DE plots, what would look the same and what would look different about them? I'm putting you on the spot, but if anybody else has an idea on this one, toss it out there. Same eigenvectors means what for the phase plane?
Would the pattern be the same, but the direction be different?
Say more about that. What do you mean by the pattern? What do the eigenvectors tell us? Remember, you're right on the cusp. You're right there. But what do the eigenvectors tell us?
Would their origins like be different?
Possibly. I'm interested in what the eigenvectors tell us. Yeah, you're coming at it from a different direction. I'm saying look at the eigenvectors. They're the same eigenvectors. So what does that mean must be true about their phase planes, their DE plots? Anybody else want to take a stab? Okay, here's what you're going to do. Take 2 minutes right now. Everybody pull up your maple. Do it for yourself. And I want you to create, use the example. Sorry, Bryce, can you pull up yours one more time so we can get a good look at what those two equations are? Write them down or type them in. The two equations are going to be dx dt equals x plus y, and dy dt equals 2x plus 2y. So you're going to make a phase plane for that system of equations. Type that in, do the phase plane. And I want everybody to do it. So
Can you do a DE plot with a matrix?
No, but you can do a field plot just to get a vector field, right? And that should be good enough. The vector field will be good enough. That might be easier if you have with plots on. That should be okay too. But go ahead and.
What were the equations again? I missed them.
It's okay. dx dt is x plus y, and dy dt is 2x plus 2y. Real basic.
Okay.
That's your first system. The second system is make everything negative. So negative x minus y, and minus 2x minus 2y.
You just want us to plot them both?
I just want you to make the DE plot for both of those. So go ahead, Bryce, you can stop sharing your screen. This is good practice, right? So once you've got that first system plotted, you're going to plot another system, and we're going to follow Bryce's lead. We're going to plot the exact same system, but everything made negative. So you can just do a copy and paste if you wanted to. So looking at those two DE plots, what do you notice?
the direction arrows are the opposite.
The direction arrows are opposite in direction, but how do they compare in terms of kind of their angles, if you want to think of it that way?
They look like they're mirror images of each other.
They're mirror images. They're
Yeah.
the same. Everything's the same, except everything is moving in the opposite direction. So what does that mean if you think of the eigenvectors? They tell us, what direction those straight line solutions are, right? So these two are two eigenvectors, these two are two eigenvectors, these two, right? So the eigenvectors tell us which direction are the straight line solutions traveling. So if they're the same for two systems, you're going to see straight line solutions that line up exactly in the same way. But if their eigenvalues are opposite, that first straight line solution might be going like this, like everything's headed out away. But if it's opposite in sign, it's going to be headed towards the origin, right? So what we have in this case is a situation where two truly different equations, sets of equations, can have the exact same straight line solutions, but can be going in opposite direction from each other, right? Towards instead of away. Does that make sense? And by the way, it works for situations where you have not straight line solutions in a traditional sense, as in they're not straight lines, but situations where you have imaginary eigenvectors. So for example, let me share my Maple screen here so you can see what I did something different, right? So I chose to make my equations 2x minus y and 3x plus 4y, and I get this phase plane, right? Clearly imaginary eigenvalues because I've got that kind of swirly business going on. But if I redo that, if I copy and paste and then I change all the signs, make that a negative, make this a positive, make that a negative, and make that a negative, and say, okay, do it this way, take a look at what I get. On the surface, you're like, oh yeah, that's the exact same phase plane. They're exactly the same. But on careful inspection, you can see, in this case, all the arrows are moving, spiraling inward. Up here, all the arrows are spiraling outward. So Austin, you were right on track when you said, is the origin going to be different? And you're absolutely right. The origin will switch. If it was a sink, a spiral sink, like this one, or excuse me, a spiral source like this one, then when you change the sign of everything, it becomes a spiral sink. Sorry, got a fly buzzing around my head here. Somebody let in a fly. Oh my God. She let it in. You let it in. It wasn't me. She let it in. Oh, you know what? The fly's buzzing around. I think it's because it smelled skunk. Austin, what did you do? Anyways. So this ties in, and I don't know if you remember, this was a question on one of the classwork sets from way back in chapter 2. If you have a system of equations that's, dx dt equals f of xy and dy dt equals g of xy, what happens if you change the sign of f of xy and g of xy? What happens if you change their signs? And we found that, it just changes the direction of all the arrows. Instead of going towards, they go away. They just change direction. And this is now, we understand it at a deeper level, because now we understand it as being, it keeps all the eigenvectors the same, exactly the same eigenvectors. It just changes the eigenvalues. So if you take a look at, go back to what Bryce had. Bryce, can you real quick share your screen one more time and show us the eigenvectors and eigenvalues that you found to begin with? Notice at the top, 0 and 3, and the eigenvectors for the same eigenvectors but opposite in sign eigenvalues, 0 and -3. So that's what it means to have same eigenvectors but opposite eigenvalues. You wind up with a phase plane that is, every arrow that was going this way is now going completely in the opposite direction. So Nice work. Good job putting that together. How do we feel about that? Did that make sense? Kind of connecting it back to something from chapter 2 as well? It's one of those that you have Maple, you can play around with it and, you know, create a system and then see what happens if you change the signs on the system. You wind up with a mirror image, right? It just looks like you just change the direction of everything. And so if you imagine a 3D plot, everything instead of moving out and away from, it would be now moving out or in and towards the origin, right? A sink to a source, depending on which direction things go. So not bad, pretty cool. Yeah, thanks, Emma. Emma was like reaching around, giving me a pat on the back. She's like, good job, Steve. You did a good job on that one. Okay. I'll take it. I'll take what I can get. Okay, how about let's take a look at 3.6 classwork exercises. For those of you who haven't seen the videos or watched the videos for 3.6, when you look through your notes, you'll notice that we get done with the notes part of it, and then there's a couple of extra pages that it says it's bonus notes. It's basically just kind of a guide for looking at the 4 types of harmonic oscillators that we've run into. There's the undamped harmonic oscillator, basic, like chapter 2 harmonic oscillator. And then there's the what happens if there's damping. It's either underdamped, critically damped, or overdamped. And so there's 4 types of oscillators, and those extra bonus notes kind of lay out kind of the story behind each one of those and what it looks like. And I didn't want to do that as a, you know, write down the notes, but you can read through it. It's good bathroom reading. You know, you got nothing to do. Just bring it with you into the bathroom. It's fun. You'll finish up in the bathroom very quickly if that's what you have to read. Trust me.
We
that's
get
a good
extra credit if we bring our notebook into the bathroom.
I don't know how you'd verify it. Well, actually, there's a way you could. No, let's not have you verify that. That's kind of gross. So speaking of number 2, let's take a look at question number 2 on the classwork exercises. That was pretty good, wasn't it? It was pretty good. I thought it was good. She didn't like it, but I thought it was good. Okay, so let's take a look at the second classwork exercise, which says if the equation from number 1 is a balanced force equation for a harmonic oscillator, mass on a spring, blah, 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 then briefly describe everything what we know about the physical context. So we're going to take this kind of real quick. I'm going to go around. John, what does the 3 in the equation tell me? It tells me you don't
Can you
have a
hear me?
microphone. Hey, now I can. Yep.
Okay.
What is the
The
3?
3?
What does that represent in the equation? You want to phone a friend? Do you want to phone a friend?
Yeah, I'd love to phone a friend.
Who are you going to phone?
Emma.
Emma. Good call. Emma, what does the 3 represent?
The 3 in this case represents the mass.
It is the mass on the spring. It's how much mass is involved with this harmonic oscillator. And John's nodding. He's like, I totally knew that. I just wanted to give Emma a chance. You know,
Thank you,
to
John.
shine.
So nice.
Yeah, sometimes. Okay, Emma, who's going next? Who's going to tell us what the 2 represents? You get to decide.
Oh,
And
geez.
you can choose John if you want. But don't, that's mean.
That would be mean. Whoever wants to answer it, I'm not going to put anyone on the spot. I'm also nice.
Okay, well, according to Emma, the 2 represents resistance.
It represents, sorry, what? I have my doggy
It
phone.
represents resistance.
Resistance. Okay. Yeah.
I did not understand that one at all, but she seemed like she did.
I used your fancy bonus notes and tried to find similarities in each case on the constants and what they were.
If you think back to, because this is our harmonic oscillator, the first term is all about mass times acceleration. The second term is something times velocity, right? And when we derive that in chapter 2 and in chapter 3, what that number represents, what that coefficient represents is the damping. You can think of it as resistance because that's really what it is. It's how much is the oscillator resisting motion. And it doesn't do a thing if it's just sitting still, right? If the mass on the spring is not moving at all, then there's no resistance. It only can resist if you give it some initial push, right? That means it has to have a velocity to resist, right? So it's the damping coefficient. Okay, Paul, who gets to tell us what the pi represents in that equation?
Well, I think Emma had one of the clues, so.
You're gonna make Emma do it? No, she's already done one. Who else? You have to decide, Paul. You choose.
Okay. Steven.
Choose your target. Who is it?
Make Steven do it.
Steven!
I'm sorry, what was the question?
He was hiding. He's like, just got a thing over here. The question is, in question number 1, what does the pi in the equation represent?
One second, let me pull it out.
That's okay. It's the...
Is that the spring constant by chance?
It is! Ding, 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 ding. The pi in that case is the coefficient of the just y, not y prime, not y double prime. It's the coefficient of y that represents the spring constant. And so that tells you what about the spring, Stephen? If you had to describe it, what would the
stiffness?
The stiffness, the oomph of the spring. So the bigger that spring constant, the harder it's going to be. Okay, now don't go crazy. The harder it is going to be to stretch it or to compress it. So if you think about it as if it's like the spring in a shock absorber, the bigger that coefficient is, the stiffer the shock absorbing is. And to help us with that, we can click on the link that's in question number 3 so we can play around with and see what happens when we vary the spring constant. We'll get to that in a second, but I wanted to tackle part B, which is, okay, now that I've already said it, everybody's clicked on it. You're like, I know, I shouldn't have said that. Now everybody's going to be doing that. How do we classify this thing as damped, or critically damped, underdamped, overdamped? We know it's damped. It's just a question of, is it over, under, or critically damped? And how can you tell? What's the magic process for being able to tell?
Okay, well, it is critically damped. And
Because?
the reason I knew that was because the 2 stood in place of the B. And I was looking on page, I think it was 63, that said when B squared equals 4, it's critically damped. And 2 squared would equal 4. So that was what I was looking.
B squared equals 4. Aha! When B squared equals 4, but it's not quite when it's just equal to 4. Let me share my screen real quick.
I think
so
it was
that
like
we can,
4 kilometers or something, or no.
let me share my screen real quick.
It's 4 times the spring constant times the mass, right?
Yeah.
Oh.
Just a reminder, we've got our m y double prime plus b y prime plus k equal, or ky equals 0. And those 3 things become the coefficients essentially in, if you remember this from before, ms squared plus bs plus k. And if that looks familiar, it's because this quadratic equation, this is the characteristic polynomial. I can't spell polynomial. There's no red squiggly underneath it. Polynomial. If there's no red squiggly underneath it, I must have spelled it right. So that means we're looking for those places for s, those s values, where negative b plus or minus the square root of b squared minus 4 times m times k all over 2 times m, where that thing, those are the s values that we're interested in. But this right here, the stuff that's underneath the radical, that determines whether we have a real repeated solution, whether we have 2 distinct real solutions, or 2 complex with imaginary part solutions. So that's the focus of whether we have critically damped, underdamped, or overdamped. And so really this thing is what we're going to use to decide. And so if b squared minus 4 times m times k, if that thing is greater than 0, then what kind of solutions are we going to have to our s equation here? If this thing underneath the radical is positive, then what does that mean about our type of solutions? You guys were in algebra class, right?
They'll be real.
Hey, this yields 2 real solutions. And if that thing is equal to 0, then that means we get 1 real solution that's a repeated solution. That's our repeated eigenvalue. Right? This is 2 real eigenvalues. This is 1 repeated eigenvalue. And if this thing underneath the radical is less than 0, then that means that we have 2 complex. Or you could say 2 imaginary, but it's not just the imaginary. It's all of that. So this is going to lead to 2 complex situations. So the question is, if you have 2 real eigenvalues, then that means you're going to have just exponential decay. That means your harmonic oscillator, there we go, your harmonic oscillator is going, and it just dies down, it just decays. If you have 1 real repeated, then it is perfectly tuned so that it reaches or it heads towards 0. So this guy right here, this is what we call overdamping, this is critically damping, and this is what we call underdamping. Because underdamping, those complex eigenvalues lead to oscillating solutions, right? They lead to a harmonic oscillator that goes overshoots the equilibrium, goes back, overshoots the equilibrium, and wobbles back and forth, slowing down, decaying, but wobbling back and forth. So typically, this is the one that we think of when we think of a harmonic oscillator. We think it's like, oh, it's going back and forth and back and forth and back and forth. It slows down because it's damped. But typically that means that we're talking about an underdamped harmonic oscillator. Your shock absorbers, if they work this way, you would go to the car, you would go to the dealership or the auto mechanic, and you'd be like, my shock absorbers are broken. Because every time I hit a bump, I go, huh, 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 huh. And you would hate that. You don't want shock absorbers that are underdamped. You want shock absorbers that are just right. You want critically damped. I suppose if you really want a stiff ride, you could make it an overdamped harmonic oscillator. But, so in order to see this, to make some sense of what's going on, and not that you haven't already, click on the link for question number 3 and head into that demo. And if you haven't had a chance to play with it a little bit, you could get to hang weights on the springs and change the spring constants. And it's a way to kind of get a really tactile understanding of what's going on. So while you guys were in your groups, I started playing around with this already. And I came up with this situation where it's wobbling, 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 where I have 2 unknown masses on 2 springs that have the exact same spring constant. So here's the question. If it's the same spring constant and there's no damping, this has been just wobbling forever here. If there's no damping and they're the same spring constant, how can I tell by looking at them which one has the heavier mass, which one is the bigger of the 2 masses? Same spring constant. How do I know which one is the bigger mass?
The yellow one?
The orange one.
How can you tell?
Orange.
Notice I didn't say which
Bigger.
one is. I said, how can you tell?
It's like physically bigger and also has a longer period.
Okay. I mean, don't be fooled by physical size. Density can make up for that, right? So you can have a smaller object that actually has more mass. It's just denser. So what were you saying, the other part that you were saying?
The period is longer.
The period
Like it
is
has
longer.
a lower frequency.
It has a lower frequency. Okay. So how does that connect to our second order differential equation? How does that show up in the solution? That's kind of the big capstone for this chapter. If we can kind of connect all that together, then we're in a good place.
Because if mass is bigger, then the velocity has to be smaller. Is that right? In order to keep the same spring constant?
Nicely done. Because there's no damping, there's no B term here.
Yeah.
The relationship between spring constant and mass is a fixed thing. And since they both have the same spring constant, the mass, the change in the mass, and there are definitely different masses, is visible in terms of the frequency. And if you read the notes for 3.6, that bonus section, you'll see the frequency for an undamped harmonic oscillator is really just the ratio of the spring constant and the mass. It's those two things kind of put in opposition to each other. By the way, this is how we can calibrate a spring balance. Right? Like you've seen in a science class. This, by the way, is how they measure the weight, the mass of astronauts on the space station. Because it's not like they can just sit in a chair and have the scale underneath, because there's no gravity. So what do? They have a contraption that is really just a fancy harmonic oscillator where the person is the mass. And so they set it into motion, and presuming it has very little, if any, damping, they can figure out what the frequency, what the period of their oscillation is. And from that, they can back calculate, because they already know the spring constant, they can back calculate the mass of the person, the mass of the object. So in space, you can't weigh yourself by traditional means, but you can use springs and oscillation like this to be able to simulate a undamped harmonic oscillator. Now, some of the other features for this particular simulation, you'll notice when you click on the original link, you have the option of like the intro, and then there were some other ones. Play around with them, because you actually get to do damping. Some of the other ones involve damping, and you can play around with that. And you can also go to other places. Like if you wanted to see what these springs would look like on the moon, this is how they would behave on the moon. Same mass, same spring, but now because the gravitational force is less, they behave a little differently. It's basically no gravity. If we go to Jupiter, higher gravity, more extreme motion. And by the way, I can stop these guys and put them into their equilibrium state. And if I'm on Jupiter or Earth, stop. You'll notice that equilibrium position is different depending on the gravitational field that you're in.
Is natural length the length without a mass?
Yeah, it is. So if I do natural length, you can see where that would be. Equilibrium position is kind of where they're at right now. And then movable line, you can actually see what happens if you set them into motion. And you can kind of say, oh, I think this one goes, so it makes it all the way down to like here. That's the bottom. And so you could measure distances and things like that with this. It's a cute little simulation. That's all that it is. It's just a simulation. And in the real world, having a harmonic oscillator with no damping coefficient is impossible. Even the least amount of friction you could possibly have in a vacuum, this thing would still have damping, because the spring, as you stretch it, is going to lose energy due to the molecules of the spring itself rubbing against each other and heating up. So
can you add damping?
Yeah, definitely. As a matter of fact, if you put the spring in a tube and then put some liquid inside the tube, then you can have basically what's called a damping or a dash pot.
I meant on the simulation.
Oh, for this particular simulation,
Like, is that
no. I'd have to jump back to one of the other screens, and I would lose you guys on the share screen. But if you click, instead of clicking on the the link. Once you click on the link, the first set of options are intro, vectors, energy, and then lab. And I think if you go into the lab, you can change the damping. There's a slider bar for the damping. So here, let me put a, here, okay, now let me share my screen so you can see what I'm talking about. Boop, boop, boop. So I've made a specific spring constant with a specific mass and a specific damping amount. And so when I bring this thing down and get it moving, you can see it starts moving. It moves, but slows down and heads towards zero. And you can see off to the side, if you were in physics, you'd be particularly interested in like energy and what's the relationship between kinetic energy and potential energy. We're not dealing with that in this class. We're mostly interested in the equation of motion. So if I make the spring constant larger and then do that, you can kind of observe what happens if I make the spring constant smaller and then do that. It heads to equilibrium pretty quickly. If I make the damping huge, this thing just like slows down to nothing. And with a big damping and a large spring constant, I can still get it to wiggle a little bit, but with a really small spring constant and high damping, it practically just heads back to equilibrium. That's what we would call pretty close to critical damping right there. And by the way, you can click on the little ruler and bring it over here and make measurements and do that stuff. It's actually designed to be the equipment that you need for a lab, like in a lab in a basic physics class. Those of you taking a physics class in the fall, you may be dealing with online labs that look like this, since you might not be able to be in a laboratory setting in the fall. So don't want to spoil the ending on that one, but you might be. That gets us through, and then by the way, that question is designed to kind of get you to play around with it, to try different things. And then of course, if you can make measurements, as soon as you can figure out what the mass is, you can figure out the spring constant. You can, if you know the mass and the spring constant and there's no damping, you can actually set up the equation of motion, right? So that gets us to the end of 3.6. There's a couple of extra problems, more practice, and we'll probably touch on them briefly on Monday. But just before we go, before we take off for the day, I want to make sure that we all are clear on what's coming up, what's due, what are we working on right now. So what should you be doing over the weekend?
Problem set 10.
Problem set 10, because that is due on Monday. I want you to get that done and turned in. On Monday, when we show up, we're going to be working on review, cleaning up any misconceptions, any problems that people are having. And then when we're done with class, and I think Monday will probably not run the whole time. I'll give you a little bit of time at the end so that you can get going and get started on the exam. That's my game plan. But you definitely want to be there on Monday so that we can tidy some things up and send you on your way to work on the exam for Chapter 3. What else should you be doing this weekend?
I have a feeling you're going to say exam review.
Oh my gosh, I'm so glad you mentioned that. On the agenda for today, I have a link for the exam 3 review. If you finish your problem set and you're looking at doing some review for the exam, that's a good place to go. Of course, you've got the classwork problems. Go back and take a look at classwork problems, a good source of review, right? Plenty to do there. And then if you run out of those, there's always the book problems that I list on the additional practice page. And if you run out of those, then you have entirely too much free time on your hands. That's all I'm going to say. So, okay, I'm going to hit stop on the record.